Hello everyone. Hope you are doing very well. So, as you all know that today we are going to start our new chapter, that is that is coordination compounds theory part 1. Okay? And today we are going to cover this NCERT section 5.1 to 5.2. So, let's begin today's topic. NCERT chapter 5 coordination compounds theory part 1, section 5.1 to section 5.2. This is disclaimer. So let's first of all discuss that how to prepare coordination compounds for JEE or NEET examination. So if you want to prepare for this chapter, what you should consider in your preparation, while your preparation, first of all, understanding the syllabus. Check the official syllabus for your exam, either JEE or NEET, and focus only on the topics that are included in the syllabus of the examinations. Key topics that you can cover from this chapter. First of all, the Werner's theory of coordination compounds, where you will discuss the primary and the secondary valence, the difference between a double salt and a complex. So you can cover these topics, which are considering as key topics to understand this chapter very well. Second thing is nomenclature of the coordination compounds. So how the formulas and naming of mononuclear coordination entities has been done, so that you can consider studying about. That is a very important topic covering under this chapter coordination compounds. Next, the key topic is to cover is isomerism in coordination compounds. So where we will discuss about various types of isomerism, like geometric, optical, linkage, coordination, ionization, and solvent isomerism. Then bonding in the coordination compounds. There are different types of bonding present in the formation of complex compounds, which is governed by valence bond theory and its limitations, also the crystal field theory and its limitations, and also how you observe the color in the coordination compounds, that you are also going to study, or you can consider it as a key topic to cover to study about this chapter. And you can also practice the questions. So like the previous year papers, solve as many as possible you can. Then some MCQs and assertion reason questions. So some examination cover the MCQs and the assertion reason type of questions, so that can also be covered under the chapter coordination compound. Practice from some standard books. Okay, so let's begin with today's objective. What is the objective of today's lecture? After attending this lecture, you will be able to understand the postulates of Werner's theory of coordination compounds, know the meaning of some important terms which is pertaining to the coordination compound. So these are the things that you are going to understand today. So let's see the topics that we are going to cover according to the NCERT in this lecture. The first include the section 5.1 called Werner's theory of coordination compounds. Then in this we will cover the example 5.1, and we will cover then our next section, that is 5.2, definitions of some important terms which is pertaining to the coordination compounds. Let's begin with the introduction. So what are simple salts? These are basic ionic compounds, basic in nature and having ionic bonding in them. So these are basic ionic compounds. They fully dissociate into the individual cations and anions when they dissolve in the water. So if you talk about simple salts, they are ionic compounds. When dissolved in water, they fully dissociate into the individual cation and anions they made up of. For example, if you take NaCl, which is considered as a simple salt, when you dissolve it in water, It will dissociate into the cations and anions fully, like Na positive and chlorine negative. Let's talk next we will talk about the double salts after the simple salts. So double salt formed from two or more simple salts. So when these simple salts combine with each other, then they will form double salts. The double salts also completely dissociate into their constituent simple ions in the solution. Okay, double salt also can completely dissociate into the constituent simple ions in the solution, which they are made up of. They lose their unique identity. For example, the double salt example are more salt. Example whose formula is FeSO4 dot NH4 whole twice SO4 dot 6H2O. Now more salt, if you consider, it will give ions in the water like iron 2 positive, NH4 positive and sulfate ion, SO4 2 negative. Then let's talk about the coordination compounds in a brief. So coordination compounds are the complex structures where the central metal ion is bonded to the surrounding molecules or ions whose you can call them as ligands via coordinate covalent bond. So there is a formation of a complex structure where there is a central metal ion and it is bonding to a number of different number of molecules or ions, and the bond is forming between the central metal and the molecules is a coordinate covalent bond, and those molecules which are surrounding the central metal ion, they are known as ligands. The coordination compounds retain their structural integrity, okay, after dissolving in the water. Complex ions when dissolved in the solution, for example, if you take K4FeCN whole 6, this complex, this dissociates into 4K positive ion and one this anion FeCN whole 6 4 negative. But the complex ion, that is this FeCN whole 6 4 negative, remains intact. Okay, so we are taking the example just to clarify this, that they retain their structural integrity. That means whatever the structure of the complex compound will be after the dissociation, after the dissolving in the solution, it will remain as it is, the structure will remain as it is. So if you take the example of this K4FeCN whole 6, it will dissociate into the 4 cations of potassium and 1 anion of this complex. Okay, so this complex is not going to dissociate further or divide further, so this will remain intact. So let's move to our first section, 5.2, definitions of some important terms pertaining to the coordination compounds. So let's see the difference between a double salt and a complex. So double salt and complex, they both are formed by the combination of two or more stable compounds in the stoichiometric ratio. So when double salt and complex, they form, so basically they both form, that means they both form by combination of either two or more stable compounds in the stoichiometric ratio. Okay, so when two or more stable compounds in the stoichiometric ratio combine with each other, they form either a double salt or a complex. Double salts are dissociate into the simple ions completely when they dissolved in water, but complex do not. This is a property or a major difference between them, that double salt, if you if you dissolve in water, it is going to dissociate into its simple ions completely. But in the case of complex, when you dissolve this in the water, it is going to remain intact. The structure of the complex is not going to dissociate. Example, carnallite, KCl.MgCl2.6H2O. This is an example of double salt. More salt, again example of double salt, FeSO4.NH4 whole twice SO4.6H2O. Potash alum, KAlSO4 whole twice dot 12H2O. complex ions such as FeCN6 negative of this complex do not dissociate into its ions further in like iron 2 plus and Cn minus ions. Okay, so these complex ions of from this complex structure can't dissociate further into its iron 2 plus and cyanide ions. Okay, this is a property shown by the complex. Meanwhile, double salts, they dissociate completely into the solution into its simple ions. General terms that are used in the coordination compounds. First is coordination entity. The species within the square bracket are coordination entities. Okay, so we just have seen the one of the example of the coordination compound, that is K4FeCN6, right? And this FeCN4 or whole 6, they are enclosed in the square bracket, right? So the species within the square bracket are known as coordination entity. So this is in this diagram you can clearly see this is the structure, or this is the formula for a coordination compound COCl3NH3 whole thrice, right? And this whole thing is packed in the square bracket. Okay, that means all the species that is present inside the square bracket, they are known as coordination entities. The ions that are present outside the square bracket are called counter ions. Now, if there is any presence of ion, either cation or anion, at the outside of the square bracket, that ion particularly will be known as counter ion. It constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. And also in the coordination entity, we have a central metal atom or ion. In this diagram, you can see cobalt is a central metal atom, so which is present in the coordination entity, and the central metal atom is bonded to fixed number of ions or molecules. Like if you take in this case, cobalt is bonding with 3 chlorine and 3 ammonia molecule. Okay, so cobalt is bonding with a fixed number of ions or molecules. Let's see some examples to understand better. So for example, we have this complex COCl3NH3 whole thrice, and this whole thing is packing or present inside a square bracket. So this is a coordination entity. The cobalt ion in this is surrounded by 3 ammonia molecules and 3 chloride ions. Similarly, this next complex nickel CO whole 4, the nickel ion is the central metal or ion which is surrounded by 4 number of carbonyl molecules, and this whole species is an example of coordination entity as it is packed inside a square bracket. Now let's see the shape wise. So octahedral, basically octahedral means the central atom or ion is the central metal or ion is connected to the 6 number of ligands, 6 number of molecules around itself. So like you can see this example of cobalt NH3 whole 6 whole 3 positive. Here ammonia 6 molecules, that means 6 number of molecules of ammonia is bonding with the cobalt, the central metal, right? So this is a example of octahedral. Similarly, COCl NH3 whole 5 whole 2 positive. Here also the cobalt is surrounded by 1 chlorine and 5 ammonia molecule. So 5 plus 1, 6. So cobalt is surrounded by 6 number of ligands, that means it is octahedral. And also COCl2NH3 whole 4 whole positive. Here also 2 chlorine and 4 ammonia is surrounded the cobalt metal, that means it is also considered as octahedral. Now if you talk about the tetrahedral, that means 4 number of ligands will be present that are directly bonded by a coordinate covalent bond with the central metal. So in this example you can see nickel CO whole 4, this whole species is present inside the square bracket, and also 4 number of carbonyl molecules is surrounding the nickel central metal, right? So this comes under the tetrahedral. Similarly, square planar, where platinum Cl4 whole 2 negative is an example of square planar structure. So these octahedral, tetrahedral and square planar geometrical shapes are more common in the coordination compound. So in the coordination compound, you see various coordination compound are either present in octahedral or tetrahedral or in the square planar geometry in the coordination compounds of transition metals. Now let's see the central atom or ion. What is it? So central atom or ion is the core of a coordination entity, is the center of a coordination entity. Coordination entity we just have discussed, the species present inside the square bracket. Okay, and the species that are present inside the square bracket, the core of that species, the center of that species is represented by central atom or ion. And this central atom or ion is core of coordination entity, and with ligands it bound to in a fixed geometry. So it bounds to number of ligands in a fixed geometry. If you take this diagram, COCl3 NH3 whole thrice, the same example, this whole thing is a coordination entity present inside the square bracket, and here the cobalt only is the central atom or ion, which is considered as a core of a coordination entity. Now let's take some examples. So for example, in this complex, nickel Cl2H2O whole 4, cobalt Cl NH3 whole 5 whole 2 positive, and the another complex iron Cn whole 6 whole 3 negative. So these are the three examples of the complex where the central atom are in this first complex nickel 2 positive, in the second complex cobalt, right? Cobalt 3 positive, and in the third complex iron 3 positive respectively. So nickel 2 positive, cobalt 3 positive and iron 3 positive are the central metal or ions, central atom or ions in these three given example of the coordination compounds. Now these central atom or ions are also referred to as Lewis acids. So they the central atom or the ion of the coordination entity, they are also referred to as Lewis acids on the basis of the electron donation or acceptance capability of them. Now let's define the another term, that is ligands. That is an important term. So the ions or the molecules that are bound to central atom or ion in the coordination entity are called ligands. Okay, so the ions or the molecules that are surrounding the central atom or ion or that are bound to the central atom or ion in a coordination entity, those ions or molecules are having a name called ligands. So again the same example, COCl3NH3 whole thrice. Here you can see if this whole thing in the square bracket is representing the coordination entity and the core of coordination entity, that is cobalt, is representing the central atom or ion, then the other things that are bounding to the central atom or ion, that is three atoms of chlorine and 3 molecules of ammonia. So they are ligands. They are bounding or they are bonding directly to the central atom or ion. Now, unidentate ligand. Unidentate ligand, uni means one. Okay, so unidentate ligand is bound to a metal ion through a single donor atom, as with chlorine negative, H2 or ammonia. What we are saying? We are saying that some ligands are considered as unidentate ligand, and unidentate ligand is having the property to bound to the metal ion through only single donor atom, as with chloride negative, water molecule or ammonia. In the chloride negative, you can consider only chlorine is going to attach or is going to bond with the central atom. So only one single donor atom is present, which is going to bound or which is going to form the bond with the central atom. Similarly, in the water, H2O, where oxygen is the single donor atom which is going to bond with the central atom or ion. Here ammonia, in the ammonia, nitrogen is only the single donor atom which is going to bond with the central atom or ion. Okay, so in the water molecule, hydrogen can't form the bond. In the ammonia molecule, hydrogen can't form the bond with the central atom or ion. Only one single donor atom is present in these ligands, so that means they are considered as unidentate ligands. Similarly, the diadentate or biadentate ligand, it can bind to a central metal atom through two donor atoms. In a single ligand, two donor atoms are present that can bind to a central atom or ion. Those ligands are considered as biadentate or diadentate ligand. Let's see some examples. Let's understand by seeing some examples. So, ethane 1,2-diamine, that is NH2CH2CH2NH2. This is the example of diadentate or biadentate ligand. In this ligand, what are the donor atoms that are present? Nitrogen atoms. Okay, so both the nitrogen atom act as donor. Both means one is this one at the leftmost side and one is this one at the rightmost side of the structure of the ligand ethane 1,2-diamine. Okay, so in the structure of ethane 1,2-diamine, the both nitrogen that are present in the structure, they both can bond with the central metal or ion, central atom or ion, to form the coordination compound, right? So that means both the nitrogen atom will going to act as donors, and that's why it comes under the example of the biadentate ligands. Next example is oxalate ion, that is C2O4 2 negative. Okay, now this ion has oxygen atoms. Okay, and both the oxygen atoms form the carboxylate groups, which is going to act as donors. So the structure, if you see, of the oxalate ion, it will be COO negative, and the C is then again connected with another C, and then that C is again connected with OO negative. Okay, so the structure is something like that: COO negative, single bond between the C and COO negative. Okay, so two CO negative species are bonding together with the carbon-carbon bond. This is the kind of structure oxalate ion have, and both the oxygen atom that are present at the end, like COO negative, so O negative, and after the formation of the single bond between carbon and carbon, COO negative. So the two negative signs that are present at two oxygen, those two oxygens both will form the carboxylate group. Carboxylate group act as donors. That means both can join or both can form the bond with the central atom or ion. So let's see the type of ligands. In this, the first is polydentate ligand. Okay, so these are important terms and these are some important concepts that you can consider to learn about. So the first type of ligand is polydentate ligand. So it is referring to a ligand that contains several donor atoms. Okay, so we have seen the type of ligands like unidentate, biadentate, now polydentate. Poly means more than two. Okay, many, or you can say. So polydentate ligand is referring to a ligand that can have or that contain several number of donor atoms in it. You can say more than two number of donor atom, because if two is present, that then we will call that ligand as biadentate ligand. If more than two atoms are present, that will going to act as donor atoms in the particular ligand. That means that will comes under the category of polydentate ligand. For example, we have this example of tris 2-amino-ethylamine, like NCH2CH2NH2 whole thrice. Okay, so tris 2-amino-ethylamine. Now this ligand has 4 donor atoms. Okay, in this 4 donor atoms are present. Which? So one is central nitrogen, which is this one, and other is 3 terminal nitrogens, which is going to be this terminal nitrogen, because it is having whole thrice. So this nitrogen is connecting with 3 chain of this CH2NH2. Okay, and in this structure, this central nitrogen and this 3 chain you can say terminal nitrogen can bound with the central atom or ion. That means this particular ligand contains 4 donor atom in it, and it can bind at multiple points, including central nitrogen and other 3 terminal nitrogens. So this comes under the example of polydentate ligand. Next, ethylene diamine tetraacetate ion. Okay, ethylene You can study like that: ethylene diamine tetraacetate ion. Short form is EDTA4 negative, and this ligand is an important hexadentate ligand. Hexa means it is going to contain 6 number of donor atoms in it. How? So it can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. 4 oxygen plus 2 nitrogen, 6 number of atoms that can bound or connect to a central metal ion and form the coordination compound. So you can see the diagram for ethylene diamine tetraacetate, that is EDTA4 negative, where N each nitrogen is connected with CH2CO negative. CH2CO negative, that means two number of this ion, that is CH2CO negative. Okay, substitute, and then this nitrogen is connecting with each other by CH2 single bond CH2 formation. Okay, so this is going to be the structure of the ethylene diamine tetraacetate, where this 4 oxygen atoms, this 1 2 3 4, at the terminal of the structure we have 4 oxygen atoms, and these 2 nitrogens to which these 4 oxygen atom group is attached. These two nitrogen atoms and these 4 oxygen atoms can attach or can bind to a central metal ion and form multiple bond, okay, at multiple points. So this is also a polydentate ligand example, and it is a hexadentate ligand. Next type of ligand is chelate ligands, or some people call it chelate ligands. Okay, so when a dia or polydentate ligand, dia means when 2 donor atom are present, poly means more than 2 donor atom are present in the ligand. So when a di or polydentate ligand use its 2 or more donor atoms simultaneously to bind to a single metal ion. Until now we are talking that if any ligand is having 2 donor atoms in it, so at a time one atom can bond with the central atom or ion, right? Although it has 2 donor atoms, both can form the bond. But at a time only one of the atom is forming, or one of the donor atom is forming the bond with the central atom or ion. But if a dia or a polydentate ligand uses all the donor atoms to bond with the central atom or ion at the same time simultaneously, then the chelate ligand will be going to form. Okay, so those structure that is going to form by the multiple bonding at the same time by 2 or more donor atoms present in a ligand, then the formation of chelate ligand will be happen. The number of such ligating groups is called denticity of the ligand. Okay, so what is the number of these ligating groups? That is considered as the denticity of the ligand. Next is ambidentate ligand. So a ligand that possessing 2 different donor atoms, where any donor atom can bind to the metal ion within the complex. Okay, so basically ambidentate ligand is a ligand which can have or which have 2 different donor atoms in the same molecule, or in the same molecular ion. The ligand is having 2 different donor atoms, where any donor atom from those 2 different donor atom can bind to the central metal ion within the complex. Okay, if you talk about the examples of such ligands of ambidentate ligands are NO2 negative and SCN negative ions. How? So NO2 negative ion can coordinate either through the nitrogen or through the oxygen to the central atom or ion present in this ligand. Okay, so NO2 means N is bonded with 2 oxygens, and through oxygen or through nitrogen, in any way it can bind with the central atom or ion. Similarly, in the case of SCN negative ion, where through the sulfur or through the nitrogen atom. Through the sulfur and through the nitrogen atom, a bond can form between the central atom or ion and this ligand. So a single ligand is having two uh, different atoms that can bond with the central metal or ion. So you can say you can see that this is example of NO2. So NO2 negative, where this nitrogen is forming the bond with the central metal or ion. Similarly, when NO2 is arranged like that, then oxygen can form the bond with the central metal or ion. Okay, the name for the compound when the bonding between nitrogen from NO2 and central metal will form, this structure or this bonding will be nitrito N, because N, that is nitrogen, is forming the bond. Similarly, when oxygen is forming the bond, then this is called as nitrito O. The other example is for SCN. So when in the SCN the sulfur is bonding with the central metal or ion, then this is known as thiocyanato S. Similarly, if in the SCN N is bonding with the central atom or ion, then this structure is known as thiocyanato N, because N is bonding with the central metal or ion. Okay, so these are the examples of ambidentate ligands. Let's talk about the next important term, that is coordination number. It is the number of ligand donor atoms to which the metal is directly bonded. Okay, so what is the number of ligand donor atoms to which the metal is bonded? That is considered as the coordination number of the coordination compound. For example, if you take this complex ions platinum Cl6 whole 2 negative and nickel NH3 whole 4 whole 2 positive, these are the complex ions you are taking as an example. The coordination number of central atom here in the platinum and the nickel in these two complex, they are 6 and 4 respectively. Why? Because in the first complex you can see platinum is surrounded by 6 number of chlorine molecules in this complex ion, right? So the number of ligand donor atoms that are present in this complex is 6. So its coordination number will be 6. In here, the second complex, nickel is the central atom. It is bonded with 4 number of ammonia molecules. That means it is bonding to 4 nitrogen atoms directly, right? Nitrogen is the donor atom in this ligand of ammonia. That means this coordination number of this complex will be 4. There is important note that coordination number is determined only by the number of sigma bonds which are formed by the ligand with the central atom or ion. So you can only consider the coordination number calculation by the determination of the number of sigma bonds that is forming between the ligands and the central atom or ion. Pi bonds, if formed between the ligand and the central atom or ion, they are not counted for the coordination number calculation purpose. Let's see the next important term, that is coordination sphere. This consists of central atom or ion and the ligands that are attached to it and that are enclosed in square bracket. So the ionizable groups are written outside the bracket. So basically coordination sphere is the square bracket area. Okay, so basically you can say in the coordination sphere the coordination entities are present, you can say that. Okay, so coordination sphere consists of the central atom or ion to which ligands are bonded and they are enclosed in the square bracket. Also the ionizable group means you can ionize that, or when dissolving in the solution it dissociates into different ion. So the ionizable group that is present in the coordination compound that are written outside the bracket, outside the square bracket, is called counter ions. So those ionizable groups that can be separated from the structure of the complex compound when it dissolved in the solution, they are written outside the square bracket and they are called counter ions. For example, if you take this example of this complex K4FeCN6, this coordination sphere is the square bracket entities, coordination entities. Okay, so square bracket FeCN6 whole 4 negative. This is a coordination sphere. Okay, how 4 negative comes? So when you remove this ionizable group of potassium, whose 4 atoms are present, 4 groups are present. So when you remove this +4 sign, because potassium is pertaining +1, right? 4 are present, so +4. When you remove this +4, here -4 will come on this complex. So the coordination sphere is this FeCN6 whole 4 negative, and the counter ion, that are ionizable groups written outside the bracket, is K positive. Counter ion is K positive. Let's see the another some important term, that is coordination polyhedron. It is a geometric shape which is made by the ligands that are directly connected to the central metal or ion. We are calling the geometric shape of the coordination compound formed by the arrangement of the ligands that are directly connected to central metal or ion as coordination polyhedron. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. These are the common geometries or coordination polyhedra that are shown by the coordination compounds. For example, cobalt NH3 whole 6 whole 3 positive. This complex is octahedral. Ni nickel CO whole 4 is, this complex is tetrahedral, and platinum Cl4 whole 2 negative. This is square planar. The figure 5.1 shows the shapes of different coordination polyhedra. So this is the figure 5.1. You can see this is the coordination polyhedra of octahedral. Okay, so this is the shape of octahedral, where there is central metal, central atom or ion surrounded by 6 number of ligands. Tetrahedral, where central metal and ion surrounded by 4 number of ligands which are directly bonding with the central metal or ion. Square planar is something like that. That means the central atom or ion is surrounding by 4 number of ligands in a particular this geometry. Trigonal, biapyramidal, where the central metal is surrounded by the 5 number of ligands in this particular geometry, right? And last one is square pyramidal, where this is the geometry for the arrangement of 5 number of ligands around the central atom or ion. So this is figure 5.1, shapes of different coordination polyhedra. M is representing central atom or ion, and L is representing a unidentate ligand. Unidentate means only containing one donor atom. Let's see the next term, that is oxidation number of central atom. So if oxidation number is the charge a central atom would carry if all the ligands are removed. So when you remove all the ligands that are directly bonded to the central atom, then what is the charge that is going to come over it? That is the oxidation number. So, and their shared electrons with the central atom. When you remove the shared electrons by the ligands with the central atom and all the ligands from the structure, then the charge that central atom would carry, that is considered as its oxidation number. Oxidation number is represented by a Roman numeral in the parenthesis following the name of coordination entity. Okay, so oxidation number is represented by Roman numeral, not by 1, 2 and 3, but by 1, 2, 3 in Roman. Okay, and after it the coordination entity names will be there. For example, if you take this complex copper Cn whole 4 whole 3 negative, here in this complex the oxidation number of copper is +1, and it is written as copper this 1 in the Roman. Okay, next term is homoleptic and heteroleptic complexes. Homoleptic complexes are the metals that is bound to only one kind of donor atoms. For example, in this complex we have cobalt and it is bound only one type of ligand, that is ammonia. 6 molecules of ammonia and it is bonding. So only one kind of donor groups are present. So this complex is homoleptic. Heteroleptic complex, the vice versa of homoleptic, that is where the metal is bound to more than one kind of donor atoms. For example, in this complex, the cobalt is bonded with the ammonia 4 molecules and 2 chlorine molecules. So different or more than one type of donor group are present in this complex. So this complex is coming under the category of heteroleptic complex. Let's see the section 5.1, the Werner's theory of coordination compounds. So we have studied some important terms which are going to be used here in the explanation of Werner's theory of coordination compound. So the postulates of Werner's theory. So the main postulates are following. First is that in the coordination compounds, metals show two types of linkages, or you can say valences. First is primary and secondary. Okay, so in the coordination compound formation, the metal, the central atom or ion show two type of linkage. First is primary and then secondary. The primary valences are ionizable and they are satisfied by the negative ions. Okay, so the linkage or the primary valence of a metal in the coordination compound, they are ionizable and they are only satisfied by the negative ions. Meanwhile, the secondary valence are non-ionizable and they are satisfied by neutral molecules or negative ions. It is equal to the coordination number and it is fixed for a metal. Okay, so also in the coordination compound, the primary valence and the secondary valence are the two linkages that it can have. Okay, so primary valence are ionizable, they can connect by the negative ions. The secondary valence are non-ionizable, they satisfied by neutral molecules or the negative ions, and they are also equal to the coordination number and it is always fixed for a metal. Then secondary linkages determine the geometry. This is the fourth postulate of Werner's theory, that the ligands that are going to attach to the metal through the secondary valencies are arranged in their characteristic spatial patterns to give a particular geometry. Let's understand the difference between the primary valency and the secondary valency. So between the primary valence and the secondary valence, the feature is, first of all, we will talk about corresponds to. So the primary valence corresponds to the oxidation state of a central atom, and secondary valence is corresponding to the coordination number of central atom. Okay, so if you know the central atom or ion primary valence, which are ionizable valence, then that is equals to its oxidation state. And if you know the secondary valence or non-ionizable valence of the central metal atom, then you know the coordination number of it. Nature, if you talk about nature, primary valence usually satisfied by the negatively charged ions, you can call it anions. Meanwhile, the secondary valence are satisfied by neutral molecules or sometimes negatively charged ions called as ligands. Ionizability, if you talk about, the primary valence is ionizable. They are ionizable valence. They can be precipitated as ions when dissolved in the solutions. For example, chlorine negative outside the bracket, if it is present, it can be precipitated into the chloride ions into the solution. So they are ionizable. Meanwhile, the secondary valency is non-ionizable, in which the ligands are directly bonded to the central metal and they do not dissociate in the solutions. Directional, if you talk about, the primary valence is non-directional, they does not dictate the geometry of the complex. Meanwhile, in the case of secondary valence, they are directional and they determine the specific geometry that the complex is going to have. For example, octahedral, tetrahedral, square planar, right? So these are the common geometries of the coordination compound shown by them. So secondary valence is directional, that means it is going to determine the specific geometry attained by the coordination complex. Next is representation. So you can represent the primary valence by the dotted lines in the Werner's original diagram. If you want to show the diagram, or if you want to draw the diagram for a complex, you can represent the primary valence of the central metal or atom by the dotted lines. Meanwhile, the secondary valence is represented by the solid lines in the Werner's original diagram. Location in the formula. So primary valence are written outside the square brackets because they are ionizable valence, right? So they are ionizable ionization sphere. So outside the ionization sphere, or you can say outside the square brackets, they are written. Meanwhile, the secondary valence are written inside the square brackets or coordination sphere. Okay. The example of primary valence is cobalt NH3 6Cl3, where the three chloride ions which is present outside the square bracket satisfy the primary valence of the central metal atom. That means it is going to tell you the oxidation number of central metal atom. So here three chloride ion are present. That means the cobalt, which is a central atom, is going to have oxidation state of +3. In the secondary valence, if you take the example of cobalt NH3 6Cl3, the same example, the 6 ammonia molecules that are directly bonded with the central metal atom, this is going to satisfy the secondary valency of this complex, and secondary valency determine the coordination number of central metal atom. So 6 number of ligands, that means 6 number of donor atom is present in this complex around the central metal atom. So coordination number for cobalt will be 6. Let's see the illustration. So in a series of compounds from in a series of compounds of cobalt +3 chloride, this +3 is in Roman, that means it is showing the oxidation state of cobalt. So in a series of compounds of cobalt chloride with the ammonia, some of chloride ions are precipitated as AgCl when you add excess silver nitrate solution in the cold, but in other case some remained in the solution. So cobalt chloride, when reacts with the ammonia, some of the chloride ions precipitate as AgCl on adding excess silver nitrate solution, but some remained in the solution. If you observe this table, if we have a compound 1 mole of COCl3.6NH3, it is going to give you the color yellow, and the moles of AgCl precipitated from it, this complex is 3 number of moles. Similarly, if you have 1 mole of COCl3.5NH3 complex, the color it is going to have is purple color, and the moles of AgCl that you are going to attain from this is 2 moles. Similarly, 1 mole of COCl3.4NH3, the green color complex, gives you 1 mole of AgCl as a precipitate, and 1 mole of COCl3.4NH3 having violet color gives you 1 mole of AgCl precipitated. If you observe, the second last and last complex are same, having same formula, but color are different, and the number of moles that are going to be precipitate for AgCl is also same. The compounds that are formulated as shown in the table 5.1, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Okay, so the compounds that are formulated in the table 5.1, we will see the table 5.1, where the atoms are present within the square brackets is going to form a single entity which is not going to dissociate under the reaction conditions. So if you see the table 5.1, the formulation of cobalt +3 chloride ammonia complexes, the yellow color compound having the formula CONH3 positive, 3Cl negative, and the solution conductivity it is corresponding to is 1:3 electrolyte. The purple color compound having formula COClNH3 positive, 2 chloride negative, the solution conductivity it is corresponding to is 1:2 electrolyte. Similarly, the green color compound COCl2NH3 positive, chlorine negative, the solution conductivity 1:1 electrolyte. The violet color compound COCl2NH3 whole 4 whole positive Cl negative. Solution conductivity 1:1 electrolyte. Now these observations together with the results of conductivity measurement in the solution can be explained as given in the table. So note that last two compounds in table 5.1, that is this one and this one, the green and the violet, have identical empirical formula COCl3.4NH3, right? COCl3.4NH3, same empirical formula, but they are having distinct properties as their color is also different. Such compounds are termed as isomers. We will talk about isomers later. Okay, let's solve an example. Example 5.1. On the basis of following observations made with aqueous solutions, assign the secondary valences to the metals in the following compounds. We have given a table where the formula and the moles of AgCl that are precipitated per mole of compounds with excess AgNO3 reaction are given. Formula is PdCl2.4NH3 and the moles that you are getting from this complex, the moles you are getting of AgCl is 2 after the reaction with AgNO3. The second formula is NiCl2.6H2, moles of AgCl precipitate is 2. PtCl4.2HCl, moles of AgCl precipitate is 0. COCl3.4NH3, moles of AgCl is 1 that are precipitated. PtCl2.2NH3, the moles of AgCl precipitated after the reaction with AgNO3 is 0. So you have to tell that you have to assign the secondary valency to the metals in these compounds. Okay, so we have just seen, or we have just studied about the secondary valency, what they represent, okay, and how can you calculate by seeing some things, by observe some things in the complex formula to know the secondary valency of the complex. So secondary valency is basically the coordination number of central metal ion. Okay, secondary valency represent the coordination number of central metal ion, and the primary valency was representing the oxidation number. So it is representing the number of ligands that are attached to it. Coordination number means the number of donor atoms that are attached to it. That means the number of ligands that are attached to the central metal ion. So the first formula includes 2 mole of AgCl precipitate, meaning 2 chloride ions are outside the coordination sphere, right? If you are getting 2 moles of AgCl after the reaction of the formula with the AgNO3, that means you are getting 2 moles of chlorine or 2 moles of chloride ion. That means the 2 chloride ions should be present outside the square bracket of the coordination complex. That means outside the coordination sphere, because the coordination sphere is not going to dissociate into its ions. Only the ions, or you can say counter ions, are going to dissolve or going to dissociate from the complex compound. So 2 moles if you are getting of AgCl as a precipitate, that means 2 chloride ions are outside the coordination sphere. Thus its coordination number will be 4. So you will just have to eliminate 2 chloride ions, and remaining ligand will be the number of ligand will be the coordination number of a central metal. Here is it is palladium, and the coordination number is 4, or secondary valency is 4. In the second case, there are 2 moles of AgCl that are going to be precipitate. That means again 2 chloride ions are outside the coordination sphere. So we will just eliminate the 2 chloride ions from the formula, and the coordination number of nickel central metal ion will be 6. Next, for the third formula, we got 0 moles of AgCl as a precipitate. That means there are no any counter ions or chloride ions that are present outside the square bracket. That means every chloride ion is present inside the coordination sphere. Thus, that will also count into the determination of coordination number. So, the coordination number of platinum central metal ion will be 6 here. In the fourth, we have got 1 mole of AgCl as a precipitate. That means only 1 chloride ion is present outside the coordination sphere. That means the coordination number of cobalt here will be 6. The sum of all the ligands present after eliminating the 1 chlorine which is outside of the coordination sphere. In the fifth formula, we got 0 moles of AgCl as precipitate. That means there are no chloride ions that are present outside. Every chloride ion is present inside this coordination sphere. So we will count them also in the calculation of coordination number. And the coordination number of platinum will be 4. Okay, so this is how you can determine the secondary valency of each and every complex. If the structure is not given proper, then you can consider the precipitate information is given, then you can consider that, and by considering that, you can calculate the number of ions that are going to present inside or outside the coordination sphere, that are going to help you in determining the coordination number of the central metal ion after calculating the number of ligands that are surrounding the central atom ion in the complex. Okay. Okay, let's cover the summary. So whatever we have been studied today we have discussed the NCERT section 5.1 to 5.2, in which we first talk about the primary and the secondary valency. So they represent the oxidation number and the coordination number respectively. Secondary linkage determine the geometry of the complex. Unlike the complex ions, the double salts dissociate into simple ions completely when they dissolve in the water. In the coordination entity, there exists central metal atom or ion, which is a core of coordination entity, to which ligands are bound to in a fixed geometry. Second thing that is present in the coordination entity is ligands. They are ions or molecules that are bonding with the central atom or ion. Then we talked about the denticity, which is the number of donor atoms present in a ligand, which can bind to a central metal atom. Diadentate ligand. So diadentate ligand has denticity 2. That means there are 2 number of donor atoms that are present in this ligand. Example is ethane 1,2-diamine, NH2, CH2, CH2, NH2. Both nitrogen will act as donor atoms here. Oxalate is another example. C2O4 2 negative, 2 oxygen will going to act as donor atoms. Polydentate ligand, that means more than 2 donor atoms is present, like in this tris 2 aminoethylamine formula, NCH2CH2 NH2 whole thrice. So every nitrogen, the central one and the terminal 3 nitrogens, are going to act as the donor atom. So 4 number of atoms are present in this, so polydentate ligand. Then we talked about the chelate ligand, whose example was ethylene diamine tetraacetate ion, which was a hexadentate ligand, EDTA 4 negative. Okay. Ambidentate ligand we have talked about, in which we have said that same ligand can contain or can bind through 2 different donor atoms with the central atom. Example includes NO2 negative and SCN negative ions. Then we talked about the coordination number, which represents the number of ligand donor atoms to which the central metal ion is bonding. Then we have talked about the oxidation number of central atom, which decides the charge of the central atom would carry, and it is going to represent by Roman numeral in the parenthesis. Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.